So practice exam. First couple questions were just kind of about functional groups. So an imine is a double bonded nitrogen. Doesn't really matter. Something like that. A tertiary amine means a nitrogen bonded to 3 carbons. So anything like that. An enamine is kind of like an enol version. Like you have an enol for enol, enamine. So you got the alkene piece, and then you got the amine piece. So those are 3. We talked about primary amines, secondary amines, enamines, aminiums. Let's go a couple of those things to know. So this is just an add the arrows. So this is maybe something you've seen, but maybe not. So just working on what bonds are broken and what bonds are formed here. And so what I was looking for, what I wanted people to see was, okay, so this first step, that adds in and that kicks that out. And what most people got that figured out, and people had a lot of trouble with this step. And they started doing some funky things, right? So everybody realized maybe that this bond needed to break, but a lot of people tried pushing electrons here. Now this carbon already has 4 bonds, so you can't give it more, you can't give it electrons, right? So the electrons needed to go the other way. And so the way you could see that is if you saw, well, wait a second, there's only one H here now, right? So the H that ended up here had to come from there, right? And then that. Another thing to look for, all of a sudden there's a lone pair there, right? And then negative charge. That's the other thing to look for. Last thing that needs to happen is that the electrons in the bond here, right, are the ones that actually take the H. Right, so it's a lot of other kind of funky things. All right, this is like, even though there's a negative charge there, the electrons are going to react in the bond, because that's what you end up with there. That lone pair is still there, so that's the final part. Biggest part people goofed up was just kind of that atom mapping, bonds broken, bonds formed. So number 3, this got a couple people too. Really was trying to make sure people were thinking about nucleophiles and electrophiles, right? Nucleophiles, electron rich, electrophiles, electron deficient. What I wanted you to recognize here was, well, what is this nitrogen? All right, it has lone pairs, and it's a nucleophile, right? And the other thing to think about, well, what was changed? I gave you the product, right? So I'm asking for this reagent. If you look here, it looks like I added 3 of these things, right? Because this ethyl piece, this 2 carbon piece, is already there. So if I broke one of these bonds and I took one step back, what would that look like? Well, the nitrogen would be there, so would the ethyl. That. All right, one of those. And then you'd have to have a lone pair here. And then something with a good leaving group there, right? Now, how do I know that, right? Again, if I'm looking at this bond, right, nitrogen's more electronegative than carbon. So if that's the bond I'm making, nitrogen's probably going to be the nucleophile, right? Not the electrophile. All right, so a lot of people try using Grignards for this. So this is the reagent. The other thing that you would have made here would have been, let's see, plus 3 H pluses, and then 3 Br minuses too, right? To balance everything out. You also make those. The 3, no, it's just 2. Sorry, just 2 H pluses, right? My fault. Just 2, because 1 Br minus is really right here. So 2 of those. All right. Some resonance with radicals. Biggest thing here is, right, just making sure you're moving the electrons to the right spots. Right, 2 electrons come together, and that forms a new pi bond. 1 electron needs to go to an atom, goes there, so on and so forth. I think I asked which was the most stable. It's probably a bad question. I don't know which one's the most stable. I would try to write a better question, but it's really about, what you're looking for stability, right? You want something that has the most substituted radical, like a carbocation, and then the most substituted alkene. So any of these secondary ones would be fine. The primary one would probably be less likely, but yeah. All right, little mechanism here. We're taking an aldehyde, and turning it into this acetal. So we got to remember that this carbon, right? This carbon right here is this carbon, right? This oxygen, this carbon's bonded to oxygen twice. This carbon's bonded to oxygen twice, right? So the first step, acidic conditions. What are we going to do? And it tells us even protonation. So we'll do PT. All right. Next step is addition. How do I know to add that? Well, I just look at the product. Obviously, this is getting incorporated and losing water. Let's add OH. Now here, a lot of folks wanted to do this to add right there, but it can't happen. You can't do an SN2, it's too bulky here, right? So now we need to do another proton transfer. And again, we're trying to make this leave, right? At the end of the day, this needs to go. That oxygen needs to go. So we're gonna do a proton transfer. Oh, what's that? Now we've made this into a water, which is a better leaving group. And now we can do eliminations, right? So a lot of these reactions you're doing, they're called addition eliminations. So if you find yourself doing an SN2, it's not with these kind of things, it's probably not right. So elim. We lost our water, but now we're gonna add again. And it can look ugly, that's okay. Doesn't need to look pretty for any reason. Let's make sure I do it right, don't lose a carbon. There it is. And don't lose the hydrogen, there's still an H there. Because the last step needs to be a proton transfer, because we noticed that's a catalyst. So the final step is that proton transfer to generate the catalyst. And we did this a bunch of ways, on and off, all sorts of things, so this should be pretty solid. So this one has no steps, but if you look, okay, there's the ketone, there's that carbon there, that's that carbon. So I need to get the nitrogen on here, and I need to lose the water and make the catalyst, and regenerate the catalyst, right? But again, H plus acidic conditions, first step is going to be proton transfer, right? So obviously it's harder without the steps, but I still think it's doable. So right, wouldn't want to do all the questions like this, but some could be like this, and that's okay. So then it adds, right? Because that's where we need to go. Once we add, make that tetrahedral intermediate. Post charge here, but we just added that. We want to lose water, so we're going to do a proton transfer. Proton transfer. Post charge there, make that a better leaving group. Nitrogen's there. Now we can do that elimination step, right? We add, eventually we eliminate. I just drew it upside down, that's okay. And then of course the last step will be that proton transfer to regenerate that catalyst, H plus. Good. So then the next one, a little something I want you to draw out this structure, all right, is very similar to NaBH4. So I wanted to make sure people really kind of understood that. So there's 3 H's on the boron, and then there's just a CN. And the boron has a negative charge. So it reacts exactly the same as sodium borohydride. But it's something you hadn't seen before, so it's just like, right, something different, but maybe recognizing it's the same. Especially since you hopefully see there's a new H there and a new H here. So what happens? H minus adds What's that going to give you? Nitrogen with a negative charge. UH. Go to step 2, right? No good leaving groups. Nothing else can happen. It grabs the H, and that gets you the final product. So yeah, I wouldn't have expected somebody to know this, but I wanted people to recognize, oh, there's Na plus, there's boron bond to 4 things. That must be a BH4. That must be like a negatively charged boron, and if I look at this reaction, it looks like an H is just adding, so it must be similar to sodium borohydride. That's why I was trying to get people to like connect 2 different things that way. So for this one, a lot of folks got, again, no steps. Okay, so it's tough. No steps to make it harder. The thing that makes this challenging is that you need to recognize, again, this carbon right here, right, is going to be the carbon, that's the carbonyl carbon. All right, that's one that's bonded to oxygen twice. So if I number these carbons, 2, 3, 4, 5, 6, the oxygens that are currently bonded to carbon 1 are going to be alcohols, right? So the piece in green is this piece, and that means this also must be an alcohol, right? So you can almost do this without the mechanism. So that means carbon 1 had to be 1, 2, 3, 4, 5, 6, 5, 6, and then OH. Now somebody might ask, well, how did you know that? Come on. I know carbon 1 has to be the carbonyl, right? That's the one. And I know that I'm breaking both of these pieces, so in this case what made it tough is that the ketone part had one of the alcohols in the same molecule. Right? I've shown you a lot of times where the alcohols are in the same molecule, but never where the ketone and the alcohol were. So then you can kind of go from here figuring this out. But there's also a way to look at this ahead of time to really help yourself draw the mechanism. So just to answer a couple questions, you don't have to do this the way I did it. I just think it's helpful to add, if you can figure out what the product is before you draw the mechanism. So you kind of know exactly where you're going. And you can't draw it as the ring. It has to, the final product for all of these needs to be aceto-bondo, aldehyde or ketone. That's what it always will end up being. That carbon 1 will always end up, in this case, carbon 1. The carbon bond to oxygen twice is the carbonyl carbon. That's what it'll end up being. All right, so I went ahead and drew all the mechanism out. Let's go through it. So we kind of did that first kind of analysis, right? I always think it's good to write those things down, right? Write down what you know. This carbon needs to be the carbonyl carbon. It doesn't matter which oxygen you actually do the proton transfer with first, which one you protonate. I did this one because I knew I had to go anyways. Protonate, proton transfer. I do an elimination, right? Got to knock it out, kick out this alcohol. Then I add in water, right? For all of these things, these acetals, right? The mass, the water that you add is the oxygen that ends up being the ketone or the aldehyde. You add in, do another proton transfer to get this to be a better leaving group. Do another elimination. And then a final proton transfer to get to the final product. Right? So you can kind of get the same, there's a lot of the same steps. Proton transfer, elim, add. Proton transfer, add a limb, or proton transfer. Right? These things are kind of happening as you're moving things to make them, right. You're making this. Why do I do a proton transfer? That makes this a better leaving group, right? So that's what I'm gonna do. And the last step always is that regeneration of catalyst. So how would we know you're making aldehyde or ketone at the end? So look at carbon 1, and you see it's bonded to oxygen twice. Okay, so that you know that's the carbon that's going to be the carbonyl, and then you see what else it's bonded to. If carbon 1 is bonded to 2 other carbons, it's going to be a ketone. If it's bonded to 1 other carbon and a hydrogen, it's going to be an aldehyde. So you look at what else the carbon that's bonded to oxygen twice, what else is bonded to? 2 carbons, ketone. 1 carbon and H, aldehyde. So this one, mechanism, I told you it's an enamine. All right, so that's good. You see a ketone and you see a secondary amine. So those are 2 things to think about. H plus is a catalyst. Looks like we're losing water. That oxygen's probably coming from there. Acidic condition. So the first step is going to be a protonation. And I got all the steps here. Seems pretty straightforward. So I'm going to go ahead and draw it all out, and then we'll talk through it. All right, so mechanism now. First thing you identify, acidic conditions. So it's going to be a protonation, proton transfer. Why do we do this? Again, we're always doing the proton transfers, the protonation of these to make this carbon more reactive. That's the electrophile. Like, again, see nitrogen's a nucleophile in these. That's part of the other thing I wanted you to remember. That you've been using nitrogen as a nucleophile, but right, so nitrogen's a nucleophile. It adds in. Do another proton transfer to make this a better leaving group to turn into water. Elimination makes it aminium. Then we do a proton transfer / elimination all at the same time, and that gets us to the enamine product. Again, same kind of beats, balancing the charges, right? Last step, we're making the H plus again. We're getting to that enamine. For this one, give the mechanism and products for this reaction. So this, at some level, you just got to kind of know what's going on. Dibol H and ester. So this is the reaction we learned. Dibol H, dibol, turns esters into aldehydes. So that means I automatically know this is one of the products. Done. Right? And actually, you actually could know the other product. It's a salt. So some people got confused about this a little bit. Al, the plus charge here, and then an O minus, like this. So that's considered one product because it's a salt, right? It's an ionic pair. It's like they have an ionic bond, so that's considered one product. Anyway, so what needs to happen though for dibol to work, right? So this is a way to add H, right? If you notice, what have we changed? We've added H. But this, unlike those other hydride sources, doesn't have a negative charge here, right? Most of the time the aluminum or the boron had that negative charge. So we got to put this in the right, we got to do some resonance first. Right? Because that gives us an oxygen with a negative charge, which then can coordinate to the aluminum. Because what that does so the negative charge is on the aluminum, and now this looks hopefully a little bit more like something you've seen before, like lithium aluminum hydride. Now the H is right there. There's only, notice there's only one H. That's right. So we go from, normally esters you add two things. This time we're only gonna add one. It's a kind of special thing. All right. And so the H adds in. All right. Add. What do we end up with? We end up with, let's see, we got an O. We got this O. Aluminum. And the final step is going to be this elimination, where the aluminum's just going to straight up fall off. And of course, we added this H. Right, this, I'll call it the blue H there. Got added, aluminum falls off. And that's how you get aluminum with a plus charge and O with a minus charge. Or you could draw them together if that works better for you. So you always have to draw out the resonance. And the reason you do is because like this isn't reactive enough by itself, right? And then also notice you get it more reactive, but then also you make it an intra molecular reaction versus two molecules trying to find each other. Now all of a sudden the hydride thing is right there. So it also helps make it go too. So have to do the resonance first. Number 10. Just trying to see if we're still paying attention here a little bit. People are like, we didn't talk about this. But like, slow down. What do we talk about, right? So you have KOH. So K plus OH minus, right? And what's that going to do, right? Well, what do we have to react with? So you probably could recognize this is my nucleophile, so this has to be my electrophile. If you look here, what's changed, right? You need to lose, right? You need to make that bond. That's a bond to break. So you could have looked at it in a retrosynthetic way. Right, this, and then, right, because if I break it, nitrogen is probably the nucleophile, and the other side would be the electrophile, right? So we see this piece would tell me these things look a lot alike, right? And I got to make an N minus. Well, OHs, NHs, SHs, and PHs. So we just have a deprotonation. Like it's at N minus, right? There's like this, and then it just does an SN2 reaction to get to the product. That's all it is. So it looks like a lot, but it's not. The question is, can we do this in one step? Why can't we? Well, first of all, it says step 1, step 2. That's the first clue. Also, if you put KOH and this there together, the OH minus might also try to do an SN2. And that doesn't lead to, you need the OH minus to deprotonate this, not add there, right?
I mean, like, so can I have my OH grab into my H, and then the bond between nitrogen and H goes into the second structure and kicks out bromine?
Gotta draw it out. Step 1, okay. Step 2. Just like in life, in an organic chemistry, there are no shortcuts. If you know where you're going, that's okay, but just slow down, draw that intermediate out, right? Because look at this is a nice intermediate. It's stabilized by resonance, right? Look at that. That's gonna be something that's gonna stick around for a little bit, maybe. TG and TM. So talk about this, a little bit of these properties. TM versus TG. So TG is when a material is like glass-like, right? So it's like brittle. When it's really cold, it's gonna get brittle. And TM was when it can't really maintain its shape and it like flows, right? Like it's not gonna not maintain its shape. So for snowboard, right, you use those in the winter. So you have to have your TG be low enough so that it's, if you're outside using it in the winter, it's cold, it doesn't crack, right? So I don't know, you could just make it up. I mean, anything below 0 would be good, because if you're doing Celsius or Fahrenheit. I have a hard time with this because I'm used to Fahrenheit for my temperatures like outside, but all my lab stuff I know in Celsius. But cold enough, low enough so it doesn't crack when I'm using it. So I would say, let's say negative 20 degrees Celsius. I don't know, right? Something like that be fine. Or Fahrenheit, who knows? Close enough, right? You want it to be, but you don't want your snowboard to be flexible but not crack, right? So like another way to think about is like tires for the TM, right? What temperature do you need your tires to be before they like start to melt on the road, right? You want them to be flexible, but you don't want them to melt, right? So your TM for that would need to be pretty high. Let's say, I don't know how hot those things get, but outside, right? My car was just sitting there, let's say 150 degrees Fahrenheit, right? Say your car's sitting there in the desert, you don't want it parked and the tires just melt because it's too hot, right? So something like that. Also, you don't want your tires to crack if it's too cold too, right? So that's a TG thing. 2 ways to make polymers more sustainable. I always think about start and end of life, right? So you want it to come from renewable sources, right? And you also want it to be able to be broken down or degradable, all right? So you don't want to use petroleum sources if possible, right? Renewable sources like plants, anything like that. But then also you want your plastics to be sturdy and work for all these cool things we use them for. But then when you're done with them, you want to be able to break them down, right? So that's really hard to actually get that, to figure that out, right? Because you want the material to be great and sturdy and strong, and then when you're done with it, you don't want it to be that way anymore. That's really tough. Cool thing, I'm like surrounded by my son's Legos. So Legos in Denmark had like a whole thing. They're trying to make their Legos out of sustainable plastics, actually using sustainable starting materials. But Legos are really hard to break down, I think. I don't know if you can biodegrade Legos or not, but things that chemists would think about and work on. So there's actually jobs at Lego. You can go work for Legos and be a chemist.